grade 12s, we're on to the second installment of graph sketching. It's just so much fun and it's about to get better. So what we've done so far has been pretty boring because they've largely been graphs that we've seen before, you know, like a straight line with a hole in it. That's nothing wild. So finally, let's start something which is a little bit more interesting. So these next three examples are all going to be quadratic functions over linear functions. Now the example we did in example 3, it basically became a straight line with a removable discontinuity, which is a bit boring. So example 4, 5 and 6 will hopefully get a little bit more interesting for us. Okay, so let's have a look at the first one. Draw the graph of h of x, which equals x squared over x plus 1. Okay, I personally like to start with my asymptotes, and so the first thing I ask myself is, before I even think about asymptotes, can I factorize and simplify? So are there removable discontinuities? And the answer to this question in this example is no. So my second thought is then to go on to my vertical asymptote, because clearly there's a denominator here, which if it's not a removable discontinuity, it is a vertical asymptote. And that in this example is x is equal to -1. This is a quadratic over linear, so the degree on top is 1 more than the one on the bottom, so this has an oblique asymptote. And for this, we can finally start looking at the idea of the limit of this now that we're going to draw the graph. So the oblique asymptote, remember, is saying, right, x squared equals x plus 1 times by something. So I'd have to multiply by x, so that would be x squared, but I'll also have plus x. Now remember, you need it to be accurate to a degree of 1 less than x squared. So plus x is not accurate. So I need a minus x so that this simplifies to x squared, which is what we've got over there. Now if I need a minus x, that means this needs to be -1. But unfortunately, the moment you put a minus x in there, you've also now got a -1, which I'm not meant to have. And so in order to make this now work, I need a +1. So +1 is my remainder. Now notice that that +1 can never equal 0. Now remember what we said. If that can never equal 0, then this graph will never cut the oblique asymptote. Now that's really important for us to think about. So I cannot cut the oblique asymptote in this particular question. So really important for us. Right, so we've got our oblique asymptote. Wait, I haven't written down its equation, so let's write it down. The oblique asymptote is y is equal to x minus 1. That thing over there. Right, intercepts would be pretty good. So intercepts, x-intercept, make y equal to 0. So 0 equals x squared over x plus 1. Now, basically, if you have a fraction equal to 0, the top has to equal 0 because the bottom's not allowed to be. So either you can think about it that way, or you can multiply both sides by x plus 1. So basically I get x is 0. So therefore 0, 0 is my x-intercept, which means, what do you know, that will also be your y-intercept. And you can check that by making x equal to 0 and what do you know. So basically 0, 0 is the only intercept we have here. And so finally, before I start looking at possibilities of this graph, I need stationary points. Now this is a quotient, and so I'm going to use the quotient rule, and the quotient rule says differentiate the top, which would be 2x, multiply by leave the bottom, subtract leave the top, differentiate the bottom, all over the bottom squared. Now in reality, the moment I hit equal to 0, that denominator is actually going to be entirely pointless in this question, simply because the denominator can't be 0. And so basically I'm going to multiply by it on both sides and it disappears. So this is actually pointless. And that's why, even though this equation looks fairly mean, it actually boils down to something really easy. So don't let these derivative questions throw you off. If I multiply by x plus 1 squared on both sides, I basically just get 0 equals the top, which in this case is x squared plus 2x. Please also remember that we never ever show working with equations as easy as this. Either, well, I suppose you can do some working if you want, but use your calculator, or you can happily just factorize in your head and solve. Now as coordinates, I know 0, 0, I've checked that out before. -2, if I sub that into h, that's -2 squared, which is 4. divided by negative 2 plus 1 was negative 1, so I get negative 4. Now, absolutely, I could go try and find points of inflection, but I always try and, at this point, to just sketch what I have so far, because points of inflection involve a second derivative equal to 0, and is that really necessary? So that will be a lot of work, so if I can avoid that work, I do. So let's just draw what I have so far. Okay, now, I've always said in class, oh, who cares about scale, it doesn't really matter. Now, the only problem here is, the only time scale does matter is when you're drawing multiple graphs on one page, and you are drawing multiple graphs here because you're drawing asymptotes as well. So let's quickly go find our asymptotes. Our asymptotes were x minus 1 and x equals negative 1. So you've got to have some sort of scale here, otherwise you might draw your stationary points in the completely wrong place. So x is equal to subtract 1. Notice I'm not measuring. When I say scale, I don't mean measure. I just mean be sensible. So x take away 1 as a line would be negative 1 there and 1 there. And so my oblique asymptote, don't forget to always write the equation on that, is x minus 1. And it goes all the way down here. Now the only other thing I know is I know that there's a stationary point and a turning point at 0, 0. And I know that there is a stationary point and not an intercept. Did I? I don't know what I said there. There's a stationary point and intercept. I hope I said that at 0, 0. And at negative 2, which would be about there, negative 2, negative 3, negative 4, about there. Now that's really important. If we didn't use a scale and we put the dot there, then we will have no idea what this graph looks like. So that's negative 2, negative 4. And that's a stationary point. Okay, now you might look at this the first time you draw this and go, okay, I have no idea what I'm drawing. Okay, but don't forget that none of us do. None of us start a question and go, oh yeah, no, that's what it looks like. You do get quite fit at these over time, but don't be afraid if you look at an equation and a graph and you're like, what? How does this look? You kind of just got to roll with it and see how it goes. Okay, so let's look at options. So let me draw options in blue. This is a stationary point. It's either a local minimum or it's a local maximum. If it's a local minimum, I have to, I suppose it could be where the graph goes flat, I suppose. I have to tend towards the vertical asymptote. So if it's a minimum and I tend towards the asymptote like that, now immediately I do that, that's not possible. Why? Because your graph is not allowed to cut the oblique asymptote. So I know it's not allowed to do that, which means it can't tend towards the vertical asymptote like that, and I'm forced to tend to the vertical asymptote like that. Okay, next thing, I suppose this could be a point of inflection and it could go up, but it has to tend to the oblique asymptote. As x tends to negative infinity, I'm going to tend towards the oblique asymptote. Now if I did that, I wouldn't be tending to the oblique asymptote, and so my graph is forced to do that. And so even though I haven't really got any idea of what this looks like, it has to look like that because the other options are not possible. Now let's look at the other part of the graph. The other part of the graph, well, this is a stationary point. So again, I could be tending towards my vertical asymptote like that. Well, no, I can't, because my graph is not allowed to go through the oblique asymptote, which means I know that I'm forced to tend towards the vertical asymptote like that. Now I get to my stationary point, so either I need to be stationary and now tend towards my oblique asymptote, or I suppose I could be stationary and go down. Now the only problem is I'm not allowed to go through the oblique asymptote. So once again, that doesn't look like my best curve, so let's try it again. I have to be tending towards my oblique asymptote as my graph, as x tends to infinity. Now you're going to get used to this particular kind of like, almost like squished hyperbola type thing. It's a very common pattern for quadratics over linears. But even if you don't get used to it, there's no other possibility that this shape could take on. So do I need to work out points of inflection? Well, no, because I know what my pattern looks like. It didn't say I had to label points of inflection. If it does, I probably would go work it out. But it looks like this doesn't have any points of inflection, because it does look like the concavity actually changes at -1 because it's concave down before that and concave up afterwards. So my concavity changes, it looks like, with the naked eye, at x is equal to -1, but that's not a point. That would be the asymptote. Now I want to take this opportunity to just discuss the idea of the limit and this oblique asymptote, because now that we've drawn one, we can actually see. So that was the graph. I worked out that the oblique asymptote was x minus 1, so it's x minus 1 divided by x plus 1 plus, and the remainder, oh no, I can't remember, the remainder was 1. Now where did that come from? I don't know if you remember the previous video on asymptotes, but that comes from the idea that you write x squared as x plus 1 times x minus 1 plus 1. And then what we go and do is we divide each term by x plus 1 to make it basically look like the graph. And so they basically got divided, those got cancelled, and so I've actually done this wrong. I don't know what I was thinking, so I clearly am not concentrating. Sorry. Thank goodness I asked myself where it came from, otherwise I'd be very confused. So basically, if I took how I found the oblique asymptote and divided by this x plus 1, I can rewrite this graph as that. Now, something I didn't explain properly previously, because we hadn't drawn it, and so it was difficult to explain. If you take the limit as x tends to infinity of x squared over x plus 1, does this limit exist? Well, that's the same thing as taking the limit as x tends to infinity of x minus 1 plus 1 over x plus 1. Now, I argued when we were doing oblique asymptotes that this would tend to 0 because 1 over infinity would be 0. And so that's why I said, there's your oblique asymptote. Now, while that's true, I never actually explained that, do we agree that this limit does not exist technically? Why? Because basically this graph is going to tend to infinity, because infinity minus 1, if it's tending towards that, infinity minus 1 is infinity. So this limit technically does not exist. So if I ask you, does the graph tend towards the oblique asymptote? Well, yes, it does. Does the limit exist? Well, no, because the limit is infinity. Infinity doesn't exist. So what are oblique asymptotes about? They're about the fact that, yes, this limit doesn't exist, but look what the graph does. It tends towards infinity by tending towards this line. So yes, it's getting bigger and bigger and bigger, and it eventually will tend to infinity. But it's behaving like it's getting closer and closer and closer to that line. So an oblique asymptote actually exists because the limit does not exist, but I'm tending towards that line, if that makes sense. So it's almost like a behavior. It's not actually a limit. So I'm not arguing that y equals x minus 1 is the limit. I'm arguing that the graph is tending towards y equals x minus 1. I hope that clears up a little bit of stuff around oblique asymptotes. Okay, that was a pretty cool graph to draw. So on to the next one. Our next one is once again a quadratic function divided by a linear function. And once again, the first thing I ask myself is, can I simplify? So if I factorize this, h of x equals x plus 3x minus 2. And while it does factorize, it doesn't simplify, which immediately tells me that I have a vertical asymptote, and that vertical asymptote is at x is equal to 1. So that's easy. The moment I did factorize, though, I can clearly see that there's two x-intercepts. And again, if I am just plotting this and I haven't actually asked for any working, I wouldn't show any working. I would say, well, when x is negative 3, y will be 0. And when x is 2, y will be 0. Now, how did I get that? Well, the only way for this fraction to be 0 is if the top is 0. And I've now factorized it, so that's really easy. So while I'm here, why don't we find the y-intercept? Y-intercept, if I made x 0, you could just go plug that in into the original 0, 0, 0, negative 6 divided by negative 1, 6. Now, while I was doing all those intercepts, I mustn't forget my oblique asymptote. Why do I know an oblique asymptote will exist here? Because the degree is 1 bigger on the top than on the bottom. So what is my oblique asymptote? Well, x squared plus x minus 6 can be rewritten as x minus 1 multiplied by, now this will have to be x, so that I've got x squared, but now I have a minus x. Now I don't want minus x, I want plus x, and I need to be accurate to x, so I need to plus 2x, because that'll give me plus x, but now that means I need a plus 2 here. But the moment I put a plus 2 there, I also get a minus 2 for free, but I can't afford to have minus 2. I need minus 6, so my remainder is minus 4. So what do you know? My graph will not cut the asymptote. So when I'm drawing this, this might help me. Sorry, that says asymptote. It looks terrible, so let me rewrite it because it looked like a squiggle. It will not cut the asymptote. That looks a little bit better. So my oblique asymptote, just to finish off my thought here, my oblique asymptote is y is equal to x plus 2. Stationary points, definitely need to work out them. So going on to stationary points, derivative, this is again the quotient rule, so we differentiate the top function, which is 2x plus 1, multiply by leave the bottom, subtract, leave the top, multiply by the derivative of the bottom, and all over the bottom squared. Now I've said this before, that bottom squared is entirely pointless, because once I make it equal to 0, the only way for this to equal to 0 is the top 0. So I would multiply out 2x squared plus x minus 1 minus x squared minus x plus 6. And this is AP math, so I'm not going to expand. I'm just going to drop the bottom. So 2x squared, this will be x squared. Plus, I have a feeling I've made a mistake, so let me just have a look. Minus, yep, you see minus 2x plus x. This is minus x, my apologies. So it's actually x squared minus 2x. And then plus 5. Now again, this is AP Maths, so I definitely don't factorize that or use the formula. I just use my calculator, and I get no real solutions because I got complex solutions, which means this has no stationary points. Interesting. Very interesting. Okay, now I would hit pause, and before I go and find points of inflection and things like that, let me just draw what I have so far. So, what I have so far, I know my y-intercept's quite high, and so I need to make sure that I can draw quite high. So, vertical asymptote is that x is equal to 1, x-intercepts at negative 3 and 2. So, if I draw that in, let's put 1 over there, 2 over there, negative 1, negative 2, negative 3, 1, 2, 3, 4, 5, 6. Unfortunately, I'm not thrilled by my scale, and so I'm only not thrilled by my scale because my y-intercept is going to be so high. So let me just make my scale on my y-axis a little bit smaller. So 1, 2, 3, 4, 5. Let's put 6 over there. So intercept so far, I know I have 2 and negative 3, and I know I have 6, and I know my vertical asymptote is that x is equal to 1, I think. X is equal to 1. My oblique asymptote is that y is equal to x plus 2. So that's going to go through 2 over there, and negative 2 on the horizontal axis. So draw my oblique asymptote. Don't forget to always label your asymptotes. So this asymptote is y is equal to x plus 2, all the way down there. Okay, now there's no stationary points. So again, you might be like, what does this graph look like? So let's just look at either sides, because remember, you're not allowed to cut a vertical asymptote. So there's kind of like two parts of this. So let's look at this part. This 2 here is intercept. Now I need to tend towards the vertical asymptote. So either I can tend towards the vertical asymptote like that. Now I know I can't do that because I can't cut the oblique. So that's not possible, which means I know I'm tending towards my oblique asymptote, my vertical asymptote like that. Now 2 is not a stationary point, so I'm not allowed to turn I'm not allowed to be stationary at all, and I have to tend towards my oblique asymptote. So I'm assuming I just carry on and I tend towards my oblique asymptote. So it's almost like a really weird looking hyperbola, no stationary points, and I only knew it was like that because I know I have to tend to my vertical asymptote, but I'm not allowed to cut the oblique. Okay, on the other side I have to go through 6 and I have to go through 3, so it's pretty obvious, and I have to tend towards the vertical asymptote, so I need to tend towards the vertical asymptote like that, and I need to tend towards the the oblique asymptote, pardon me, and there's no stationary points. So that looks like, again, it's almost like the other, in a way, this is almost like the opposite of the previous. So the previous one looked like that, so it was kind of like a squished hyperbola, and this is almost like the other kind of, I don't know, distorted hyperbola, which is pretty cool. So I'm not going to bother finding points of inflection because I don't actually think my concavity changes other than at 1. I think before 1 it's concave up, it looks like, it might not be, and above 1 it looks like it's kind of concave downish, although I don't know, yeah, it looks like it is. So that's pretty cool. Again, I would have no idea what this graph looks like until I actually plot everything on the graph and then kind of figure out what it has to look like, because there's no other option. Man, isn't this fun? Okay, last one for this video. Another quadratic over linear. Draw a graph of x squared plus 3 over x minus 1. Can you simplify? Well, definitely not, because x squared plus 3 is not factorizable. So moving on, asymptotes, absolutely. X is equal to 1 is a vertical asymptote. Oblique, there will definitely be an oblique asymptote because the degree on the top is 1 bigger than the one on the bottom. So oblique, just write myself a note, x squared plus 3 is equal to x minus 1 times what? Well, it must be times x, but then you would get x squared and you'd also have minus x, which I don't want. I'm actually not allowed any x's. So I need to plus x, so this actually needs to be plus 1, so that I get plus x, but then unfortunately I also get minus 1. Now I'm not meant to have minus 1, I'm meant to have plus 3. So as far as I know, that's a plus 4. So let me just close my bracket there. Now again, none of these so far are hitting the oblique asymptote. So this tells me I'm not going to cut. And you've seen how useful that concept has been so far. So not cutting the oblique asymptote today. So what is my oblique asymptote? There it is. It's y is equal to x plus 1. So my oblique asymptote, y equals x plus 1. Intercepts. X-intercept would mean y would equal 0. Now, I don't think that's going to yield any fruit because x squared plus 3 can't equal 0. And x minus 1 is not likely to equal 0. So this has no solution. So there's no x-intercepts, which is interesting. Y-intercepts are generally easier to find because you just make x 0. And when x is 0, 0, 0, I'll get negative 3. So, lastly, stationary points until I'm worried about points of inflection if necessary. But stationary points, I need to find my derivative, which again is the quotient rule. So differentiate the top, leave the bottom alone, minus, leave the top, differentiate the bottom, all divided by the bottom squared. Now, you can't not write that bottom squared, but the reality is it's not going to play a role. So 2x squared minus 2x minus x squared minus 3. Notice I've dropped my denominator, so I get x squared minus 2x minus 3. Again, we don't actually show any working. We just punch that into your calculator and you get the answers. So in this case, the answer is 3 or negative 1. So if we find the y values at that point, because don't forget that this is a coordinate, so 3 would be 3 squared is 9, 9 plus 3 is 12, 12 divided by 2 is 6, and negative 1 would be negative 2, I think. Right, again, I'm going to draw this quickly before I worry about any intercepts or anything. I mean, any, what are they called? Points of inflection. Because if I don't have to work them out, I prefer not to work them out. Right, so what have I got so far? Right, axes. Again, I have to draw a turning point at 6, and so maybe I should try and make my vertical axis not so hectic. So vertical asymptote is that x is equal to 1. There we go, x equal to 1. No x-intercepts, as we said. -3, so if we make that -1, -2, -3, at -3, this is a y-intercept. There we go. My stationary points were at 3, 6, so 1, 2, 3. If we make it 1, 2, 3, 4, 5, 6, so that'll be round about there. So let's label that. So that is a stationary point. So 3, 6. -1, -2 is the other stationary point. So -1 will be about there. -2, -1, -2. Oh, that looks terrible. That looked like illegible. So let's try again. -1, not much better. Please forgive me. There we go. That would be about -1. And the only other thing I think I have to add in is my oblique asymptote, which is y is equal to x plus 1. So that would go through 1 and -1. And that's why you can see that scale is so important here. I mean, rough scale. You notice I haven't been pedantic, but a rough scale is important because seeing that that stationary point is below that oblique asymptote is really important. And now why I chose to do this one is to convince you that you start getting really good at this because you start recognizing patterns. So this is a stationary point and I have to go through there. Well, I'm not allowed to go through my oblique asymptote, so I need to tend towards my oblique asymptote, and I clearly need to tend down and tend towards my vertical asymptote. There's no other ways that that could work without going through the wrong intercept or going through the oblique. And same thing here. That's a stationary point, and there's no ways I can do that because I'll go through the oblique. So I have to be tending towards the vertical, and I have to be tending towards the oblique. And so you'll notice that that's the same pattern that we figured out an example for. So basically we've seen kind of almost two types of patterns here with these oblique asymptotes with the quadratic divided by the linear. It really has been fun, and I hope that you've realized that you do not have to know what this graph looks like before you've plotted everything and kind of fumble your way through what it's forced to look like by the information you have. Cool. We still have quite a few graphs to draw, but another time, let's not do all the fun things at once. And I think we need to pause and practice some of these as well. Cool. Well done.